Welcome to another deep dive. We're going electrical today.
That's right. Getting into the nitty-gritty of circuits.
Yeah, the stuff that makes our gadgets tick, even things like pacemakers. You brought some fascinating stuff on how circuits with resistors and inductors or capacitors behave those first-order circuits, right?
Exactly.
We're going to explore how they respond naturally, like when there's no power source constantly pushing them.
Yeah, think of it like this. You give a swing a push and let go. That's what we're talking about.
Makes
I
sense.
want to break down the core principles of this natural response, nice and clear, without getting too technical.
Okay, so let's start with the basics. What exactly is this natural response we're talking about in electrical circuits?
Well, it happens when the energy stored in an inductor or a capacitor is suddenly released.
Suddenly released. How?
Imagine it's been connected to a DC source, storing up energy.
Right.
The natural response kicks in when that source is abruptly disconnected,
I see.
like cutting the power. That stored energy has to go somewhere. It's
Mhm.
released into a network of resistors.
So the circuit's basically on its own now, with just resistors and either an inductor or a capacitor.
Exactly. And all that pent-up energy starts to dissipate.
And the behavior at this point is determined entirely by the circuit's components themselves.
Absolutely. No external forces acting on it. It's all about how that stored energy redistributes and eventually fades away within the circuit.
Fascinating. Let's dive into a specific example then. Say we have an inductor and a resistor and RL circuit. How does the natural response play out?
All right, picture an inductor. It's been storing energy because of the current flowing through it.
Got it.
Now, when we remove the source, here's the thing. The current through an inductor, it can't change instantly.
Oh, why not?
It's got this kind of electrical inertia, if you will.
Nothing
Instead of
so-
just dropping to zero, it gradually decreases.
Okay.
That stored energy in the inductor, which is in its magnetic field, starts to dissipate as heat in the resistor.
So the inductor is kind of resisting the sudden change in current.
Yes. And that resistance creates a voltage
Oh,
that drives the current through the resistor, where the energy is then lost as heat.
so it's all connected, the current, the inductor, the resistor.
Right, it's like a chain reaction. This resistance to change comes from the magnetic field the current created in the inductor.
And how do we actually describe this behavior mathematically?
Well, we look at the relationship between the voltage across the inductor, which is proportional to how quickly the current changes, and the voltage drop across the resistor, which is proportional to the current itself.
Okay.
And that gives us an equation, a first-order differential equation.
Differential equation. Sounds a bit intimidating, but I think I get the idea. What's the takeaway from solving this equation?
The solution tells us that the current in the circuit decays exponentially over time.
Exponentially.
Yes. It starts at its initial value, the current just before the source was disconnected, and then it gradually decreases towards zero.
So like a curve that gets flatter and flatter over time.
Exactly. And there's this important concept called the time constant, denoted by the Greek letter tau.
Time constant.
It essentially tells us how quickly the current decays.
Okay, so how do we calculate this time constant for an RL circuit?
Simple. It's just the inductance, L, divided by the resistance, R.
L divided by R. Got it.
Yep.
And this time constant is measured in?
Seconds. It's basically a measure of how long this transient behavior lasts, the period of change.
So if we had a larger inductor or a smaller resistor, the time constant would be larger, meaning a slower decay.
You got it. After one time constant, the current drops to about 37% of its initial value.
37%, huh?
It's just how exponential decay works. And after about 5 time constants, the current is practically zero. This period of change is called the transient response.
Transient response, okay.
And eventually, when the current settles at zero, that's the steady state response.
Mhm.
Nothing's changing anymore.
Makes sense. So the voltage across the resistor would also be changing in a similar way, wouldn't it?
Absolutely. Since the voltage across the resistor is directly proportional to the current flowing through it, it follows the same pattern.
Same exponential decay, same time constant.
You got it. As the current decreases, so does the voltage across the resistor.
Now, what about the energy that was initially stored in the inductor? What happens to it during this natural response?
All that energy, well, it ends up dissipated as heat in the resistor.
So it's not lost, it's just transformed into another form of energy.
Exactly. It's like the energy is slowly bled off through the resistance, converting into thermal energy.
You mentioned an example earlier, a 2 Henry inductor with 20 amps initially connected to a 10 ohm resistor. What would the time constant be in this case?
Let's see, the time constant would be 2 henries divided by 10 ohms, which gives us 0.2 seconds.
0.2 seconds. So the current would decay exponentially from 20 amps, reaching about 7.4 amps after one time constant.
Right. And after about a second 5-time constants, it would be nearly zero.
Interesting. And you also mentioned something about graphically estimating the time constant.
Oh, yes. If you plot the current decay over time, you can draw a tangent line to the curve at the very beginning, at time t0.
At the very start of the decay.
Right. That tangent line will intersect the time axis at a point that's exactly 1 time constant away.
Wow, that's a neat visual way to understand the rate of decay.
It is.
Okay, so we've covered the natural response of an RL circuit. What about an RC circuit with a resistor and a capacitor? How does that behave differently?
It's similar in concept, but instead of the current, it's the voltage across the capacitor that can't change instantly.
Oh, so now we're focusing on the voltage across the capacitor.
Exactly. Imagine a capacitor that's charged to a certain voltage, meaning it's storing energy in its electric field.
Right, like a tiny battery.
When it's connected across a resistor, the voltage across the capacitor doesn't just suddenly drop to zero.
It gradually decreases, right? Like with the current in the RL circuit.
Exactly. The stored energy in the capacitor dissipates as heat in the resistor.
And I'm guessing this behavior is also governed by a first-order differential equation.
You bet. This time, it relates the current flowing through the capacitor, which is proportional to how quickly the voltage across it is changing, and the current through the resistor, which is proportional to the voltage itself.
And the solution? Does it also show an exponential decay of the voltage?
Spot on. The voltage across the capacitor decays exponentially from its initial value towards zero.
And what about the time constant for an RC circuit? Is it calculated differently than for an RL circuit?
It's a little different. For an RC circuit, the time constant is the resistance, R, multiplied by the capacitance, C.
R times C. So a larger resistance or capacitance leads to a slower decay, just like with the RL circuit.
Exactly. And after 1 time constant, the voltage will have dropped to about 37% of its initial value, just like before.
It's interesting how that 37% keeps popping up.
It's just a characteristic of this type of decay.
And I assume the current in the resistor also decays exponentially with the same time constant.
Precisely. Since the current is determined by the voltage across the capacitor divided by the resistance, it follows the same decay pattern.
So as the capacitor discharges and its voltage decreases, the current also diminishes.
Right. It's all interconnected.
And what about the initial energy stored in the capacitor? Where does that go?
It's eventually dissipated as heat in the resistor as the capacitor discharges. No energy is truly lost. It's just transformed.
Okay, let's take another example, similar to the RL circuit. Say we have a 0.5 microfarad capacitor charged to 100 volts, and we suddenly connect it to an 80 kilo ohm resistor. What happens then?
Okay, so the time constant in this case would be 80 kiloohms times 0.5 microfarads, which gives us 0.04 seconds, or 40 milliseconds.
40 milliseconds.
The voltage would then decay exponentially from 100 volts. After 40 milliseconds, it would be down to about 37 volts.
Got it. And like with the RL circuit, we could also graphically estimate the time constant by plotting the voltage decay and drawing a tangent line at T0.
You've got it.
It's amazing how these simple circuits have this predictable decay behavior governed by the time constant.
It's like each circuit has its own signature based on its components.
You mentioned pacemakers earlier and how they use RC circuits.
Yes, that's a perfect example of this concept in action.
It's actually generating the electrical impulses that keep the heart beating, right?
Exactly. Knowing how the capacitor discharges is crucial in designing the timing of those impulses.
So if you wanted a heartbeat of 60 beats per minute, that means a cycle time of 1 second. The RC circuit and the pacemaker has to be designed so the capacitor discharges and recharges within that 1 second window.
Precisely.
Yeah.
It's all about controlling that time constant. A smaller time constant would mean faster discharge and potentially a faster heart rate. A larger one would slow it down.
Wow, so the time constant is literally dictating the pace of a heartbeat. That's incredible. These natural responses, they're not just theoretical, they have real-world consequences.
Absolutely. They're at the heart of so many technologies.
So we've explored how these first-order circuits behave naturally when their stored energy is released.
Yep.
But what happens if we actively drive them with a sudden DC voltage or current?
That's the step response, right? Exactly. It's like giving the circuit a sudden jolt of energy.
Okay, so we're no longer just passively observing the circuit's natural behavior, we're actively pushing it. What's the fundamental difference with this step response?
We're introducing a constant DC source, either a voltage source or a current source.
Right.
And we're suddenly applying it to the circuit, like flipping a switch.
I see.
So now the circuit isn't just releasing its own stored energy.
It's interacting with this new energy source.
Exactly. And it still has its resistors, inductors, or capacitors to deal with.
So it's a more dynamic process.
Absolutely. The circuit has to respond to this sudden change in input.
Like it's trying to figure out a new equilibrium.
Exactly. It moves from its initial state towards a new steady state determined by the applied DC source and the circuit components.
Interesting. Okay, let's start with the step response of an RL circuit. Imagine we have an inductor, maybe with some initial current, maybe not.
Okay.
And then we suddenly connect a DC voltage source in series with a resistor and that inductor. What happens?
When that voltage source is connected, the sum of the voltages across the resistor and the inductor must equal the applied source voltage, according to Kirchhoff's voltage law.
Makes sense.
And this gives us another first-order differential equation. But this time, it includes that constant voltage source term, making it what we call non-homogeneous.
Non-homogeneous because of the constant external force, right?
Exactly. Now, solving this equation for the current, we see it exhibits either an exponential rise or an exponential fall.
So it depends on whether the initial current was lower or higher than the final steady state value.
Exactly.
And what determines that final steady state current in the RL circuit?
In this case, with a DC voltage source and a resistor in series with the inductor, the final current will be the source voltage divided by the resistance.
So once the inductor settles down, it's just like a simple circuit with a voltage source and a resistor.
Yep. The inductor eventually behaves like a short circuit in the steady state, so it doesn't affect the final current.
Makes sense. And does the time constant, LR, still play a role in how quickly the current reaches this steady state?
It sure does. It dictates the rate of change. After one time constant, the current will have reached approximately 63% of the difference between its initial and final values.
So it's not just about decaying to zero anymore. It's about approaching a new value determined by the source.
Precisely. And the time constant tells us how quickly that happens.
And what about the voltage across the inductor during this process?
Well, initially, when the source is connected, there might be a sudden change in the inductor voltage.
Right, because the current is trying to change rapidly.
But as the current approaches its steady-state value, the rate of change decreases, and so the voltage across the inductor eventually decays to zero.
So the inductor is only fighting back as long as the current is changing. Once things settle down, it stops resisting.
You got it.
Okay, let's work through an example. Say we have an 8-amp current source connected to a 200 millihenry inductor for a long time.
Yep.
Suddenly, we switch it up. We remove the current source and connect a 24-volt voltage source in series with a 2-ohm resistor to that inductor.
Sounds like a fun experiment.
What happens to the current and voltage in the inductor after this change?
All right, let's break it down. Initially, the inductor has 8 amps flowing through it, right?
Right, because it was connected to that 8-amp current source for a while.
Okay, so now with the new setup, the final steady-state current is going to be 24 volts divided by 2 ohms, which is 12 amps.
12 amps, got it.
Now, the time constant for this new circuit is 0.2 henries divided by 2 ohms, which is 0.1 seconds.
0.1 second. So
Yeah.
the current is going to rise exponentially from 8 amps towards 12 amps with a time constant of 0.1 seconds.
Exactly.
And what about the voltage across the inductor?
Well, right when we make the switch at time t0, the voltage across the inductor will be 8 volts.
8 volts.
And from there, it'll decay exponentially to zero as the current settles at its new steady-state value of 12 amps.
So again, the inductor initially pushes back against the change in current, but eventually it gives in.
Precisely. It's like a temporary resistance that fades away.
So the big difference here, compared to the natural response, is that the current doesn't decay to zero, but instead goes towards a new value set by the source.
Exactly. It's being driven by that external source now.
Okay, let's move on to the step response of an RC circuit. What happens if we apply a DC voltage or current source to a circuit with a resistor and a capacitor, which may have some initial voltage?
It's a similar story to the RL circuit.
Okay.
The voltage across the capacitor is going to show an exponential rise or fall.
Towards a new steady state value, I assume?
Exactly.
And what determines that final voltage across the capacitor?
Well, it depends on the specifics of the circuit, how the components are arranged, and of course, the value of the source.
So it can be a bit more complex than with the RL circuit.
A bit, yeah. But the key is that once the capacitor reaches steady state, it acts like an open circuit.
An open circuit, meaning no current flows through it.
Exactly. So the voltage across it will depend on how the rest of the circuit is configured.
I see. What about the time constant for an RC circuit during this step response? Is it still just R times C?
Yep. still the same time constant.
Yeah.
And it still governs the rate at which the voltage changes, moving towards its final value.
And the current flowing through the capacitor during this step response, how does that behave?
The current in the capacitor, it's proportional to the rate of change of the voltage across it.
So at the very beginning, when the voltage changes rapidly, there's a large current.
You got it. But then, as the capacitor voltage approaches its steady-state value, the rate of change decreases.
So the current eventually dies down to zero, just like the voltage across the inductor in the RL circuit.
Exactly.
Let's go through an example with an RC circuit. Say we have a capacitor that initially has 0 volts across it.
Right.
We then close a switch, connecting it to a resistor in series with a 10-volt DC source. What happens to the voltage and current?
Okay, so the initial voltage across the capacitor is 0, right? And the final steady-state voltage, since the capacitor is in series with the resistor and the 10-volt source, will be 10 volts.
10 volts.
Now, the voltage will rise exponentially from 0 towards 10 volts with a time constant of RC.
Right.
And the current, well, it'll start at a maximum value of 10 volts divided by the resistance, and then it'll decay exponentially towards 0.
So the voltage is increasing, the current is decreasing.
Right. Just like with the RL circuit, but the roles are reversed.
You mentioned earlier this general approach of using the initial value, the final value, and the time constant to analyze these circuits.
Yeah.
It seems like a really powerful way to figure out what's going on without getting lost in the math.
It is. Identifying those 3 key values, the initial value, the final value, and the time constant, gives you a roadmap for the circuit's behavior.
So whether we're looking at a circuit releasing energy or responding to a sudden input, this framework helps us understand its dynamic behavior.
Exactly. It's a way to make sense of these complex processes.
Well, we've certainly gone deep today into the natural and step responses of first-order circuits.
We have.
It's fascinating how these combinations of resistors, inductors, and capacitors lead to these predictable exponential behaviors. And that time constant, it's really the key to understanding it all.
It is. It governs the whole show.
From pacemakers to countless other applications, these principles are fundamental to electrical engineering.
They really are the building blocks.
Thanks for diving deep with us today. We hope this exploration has been enlightening.
Thanks for listening.